Thank you to the organisers for the invitation to this very nice meeting. I guess like a lot of people, when I got the invitation, I was quite perplexed by the title of the meeting. So my talk is going to be about something that I call synthetic probability theory. So it's very much on the synthetic mathematics side. But there seem to be three topics of the meeting, and when I received the invitation, I had no idea what they had to do with each other. And I must admit, I wasn't even sure what the middle one was, the logic-affine computation. So my talk is going to be really pretty much squarely in the left-hand camp of synthetic mathematics. I'll say a little bit about proof systems, and I'm going to get the word affine into the talk in one place. Right, so I mean, for me, the motivation, which is a very personal one, was just to do with trying to learn probability theory and understand it. And when you read through kind of more advanced proofs in probability theory, I mean, at least the impression I always got is there's a sort of separation between two lines of reasoning. One is the nice mathematical reasoning involving like computation, some arguments from analysis, this kind of stuff, which really seems to be focusing on the core of the issue and establishing the probabilistic bounds and this kind of thing. And the other is that there's a whole lot of rather complicated set theoretic superstructure there, or infrastructure, if you don't know which word is best in the context, that according to the usual presentations has to be there to make things work, but one wonders if a lot of it could be done away with by a nicer presentation. And so the aim of this talk is to provide a set of axioms for doing probability theory in a different way. And so getting rid of the usual set theoretic infrastructure or superstructure, as I say, I don't quite know which one is the best word. So trying to more focus on the constructions and results in purely probabilistic terms. And so I view this as a synthetic approach to probability theory, in that I'm going to have some axioms, and the idea of the axioms is they're extrapolated from a sort of synthetic view of what probability is. That's one's looking at the probabilistic experience and making a mathematical idealization of that. So this is synthetic in the synthetic analytic tradition, in which one's looking at truths and constructions of probability theory as kind of contingent truths about the experience of probability theory, rather than obtaining them as analytic, unavoidable facts as a result of some set theoretic definitions that don't seem that well connected at first sight with the probabilistic intuitions. Anyway, that's kind of the motivation. Obviously, the talk's going to be more on the technical side, and the real, I think, main technical innovation of this approach is that in probability theory, as done by probability theorists, the notion of random variable is really the central notion. And the idea here is to take random variable as a primitive notion and axiomatize that in terms of what one can do with random variables. So this side, I have a computer science background, and this side is a bit motivated by a methodology from computer science, where one likes to have what are called abstract data types, descriptions of data types in which you describe the data type you've got in terms of the interface, what you can do with it, rather than the specific concrete implementation. So in this respect, ordinary probability theory in the standard analytic tradition of mathematics would correspond to having a set theoretic definition, that is, implementation of the notion of random variable. And here we're going to concentrate on the interface instead, what one can do with random variables. So I call this, I think this is it's fair to call this a synthetic probability theory because it seems to be synthetic mathematics in the spirit of other such subjects, such as synthetic differential geometry or synthetic algebraic geometry that we heard about yesterday. However, in recent years, people have started using synthetic probability theory to mean other things. So this talk's not to be confused with synthetic probability theory in the sense of Tobias Fritz, which is actually a very prominent approach to category theoretic probability theory now, based on essentially doing probabilistic reasoning using string diagrams to define what one might call probabilistic maps, or technically Markov kernels. So I think, another approach which is related to the previous, to doing what people are also calling synthetic probability theory, or sometimes synthetic measure theory, is being undertaken by Sam Staton from Oxford and his group, which is similar to the previous, but they focus a little bit more on having programming language where programs define probability distributions or more generally measures. So these are synthetics in senses that they can motivate, but it's kind of different from my approach because I'm really focusing on random variable and I'm trying to provide a synthetic theory in the sense of a single axiomatization which suffices for developing the results and constructions of probability theory. And just actually one thing I didn't emphasize here is, so I'm going to give some axioms, and I believe, I believe they provide a simpler and more perspicuous way than the usual ZFC-based mathematical approach to doing probability theory. So this is my connection with efficient proof systems, if you like. I'm sure it's not the sense that efficient proof system is meant, but there's a proof system here, the underlying logic, there are some axioms, and I'm trying to make the proofs efficient in the sense that they're simpler and more perspicuous. Okay, so the talk is synthesizing random variables, and that's the title. I chose that for two reasons, because on the one hand, I'm going to talk about how I came up with the axiomatization. So the first part of the talk is going to be about synthesizing the axiomatization itself, so discovering the axioms. And I'm going to present that by essentially telling the story of how I developed the axioms, including some wrong turns I took. I mean, I don't know how interesting this will be, but I think in retrospect it was, to me, a little bit interesting. Just if you're developing a synthetic subject, there are various kind of options to take, and how do you choose which way to go? And so I thought it might be interesting to tell you something of what happened. But then there's a second half of the talk, which is once we've got the axioms in place, it's just using them. And one of the main things you use axioms for in probability theory is, to prove results, but you want to prove results about some actual probabilistic scenario, and to get the probabilistic scenario you need to define the random variables that are involved in the probabilistic scenario. So I'm going to show how the axioms provide the tools for synthesizing the random variables that you need in probabilistic arguments. My hope is to get on to Brownian motion as a non-trivial example here, but we'll see how the time goes. I had plenty of time in theory for presenting this talk. I don't have the same excuses as some of the speakers legitimately had yesterday, but somehow in the end I left things a bit to the last minute. And so normally when you prepare a talk, you should go through a phase of building up the content and then another phase of paring it down to what will fit into the time. I didn't quite get to the second phase, so I may just have to speed up at some point during the presentation. Well, we'll see. Anyway, I'm going to tell you the story of how I came up with the axiomatization as an approach to trying to tell you what the axioms are. And there's a kind of general maxim that one might take as a guide for developing a synthetic theory of a branch of mathematics, which is to have a well-chosen model and to try and extract the axioms from that well-chosen model. So the clue to the well-chosen model starts off with, well, we want to abstract the notion of random variable. We want to primitive notion of random variable. So let's start with the ordinary notion of random variable from standard probability theory and see where it takes us. So a real valued random variable is already quite a clunky definition. There's a lot of ingredients to it. You have a sample space, which is where your probability resides. So to be general enough to have arbitrary continuous random variables, you want your probability space to be a measurable space with a probability measure. And then in order to be able to assign probabilities to the sets you're interested in, you want your random variable to be a function that assigns to your sample points in the sample space. That's probabilistically generated things happening. Maps those to random variables, and then you want to be able to assign probabilities to nice sets. So typically in probability theory, one takes the nice sets to be the Borel sets. And so we want every Borel set to be its inverse image to be a measurable set according to the sigma algebra in the measurable space. And nicely, random variables form a pre-sheaf where the index category for the pre-sheaf is the category of probability spaces. So if you consider the set of random variables over the sample space omega, and you've got a measure-preserving map from another sample space omega prime into omega, then you can simply, by composition, re-index the random variable along the measurable map to get an equivalent random variable over the sample space omega prime. So that gives you a pre-sheaf from that's a pre-sheaf over potentially the large category of probability spaces. It's nice to have pre-sheaves on small categories. And also, arbitrary probability spaces have lots of mathematical anomalies. It's just like the category of all topological spaces. There are lots of very weird topological spaces. There are lots of very weird probability spaces. So I'm going to restrict to a very small category of very nice probability spaces, which is now quite standard in people doing category theoretic probability theory, which are the probability spaces is known as standard Borel probability spaces. So that's essentially completely metrizable topological spaces with the Borel sigma algebras. But it doesn't, for the purposes of this talk, doesn't matter too much exactly what that concrete category is. What's important is that they're nice sample spaces. Okay, so that's kind of straightforward that we have a pre-sheaf. But one of the nice things about restricting to the category of standard Borel probability spaces, so one of the nice properties that they enjoy that arbitrary probability spaces don't enjoy, is that if you have any co-span, so like a pair of maps into the same object, you can complete that co-span to a commuting square. Actually, you can do it in quite a canonical way. And that property means that the atomic Grothendieck topology is defined on this category. And what I noticed in 2013, and this was what got me started, so I've been working on this for a long time, and this is what got me started on this project, is that actually the pre-sheaf of random variables is actually a sheaf for the atomic topology, as long as you identify random variables up to probability 1 equality, so almost sure equality. I'm not going to go through the details of this, but the intuition here is that if you have a random variable over a large sample space that actually only depends on a fragment, on the variation available in a fragment of that sample space, actually that random variable cuts down to the smaller sample space. You can phrase that as you can formulate that as a sheaf property. Anyway, so we have that random variables, at least identified up to almost sure equality, form an atomic sheaf. And so I started this theory by taking this category of atomic sheaves over standard Borel probability spaces as the model. It had some nice properties. So it's a Grothendieck topos, of course, because it's defined as a category of sheaves. It's Boolean. So in fact, as well as modeling, it doesn't just model intuitionistic higher order logic, it models classical higher order logic. The full axiom of choice fails in the internal logic, but the axiom of countable dependent choice holds, which is kind of the axiom you really need to do a lot of analysis. And more importantly, as we've just seen, it contains a sheaf of random variables. In the previous slides, I was just looking at real valued random variables, but an analogous definition defines a sheaf of A-valued random variables for any standard Borel space A. And so I thought this is a nice model because it's a sort of model of higher order classical logic with dependent choice. It's got the sheaves of random variables, which we can take as our objects of kind of primitive random variables, so we can explore their properties in this category. So the idea is to take this as consider this for the axiomatization. We're going to consider this as our ambient category of sets and work in its internal logic and add appropriate axioms for the random variable objects. And then my first thoughts at this point about trying to understand this category were, well, let's find out more about the category theoretic structure of this category. And so one thing that leaps to the attention, if you know some pre-sheaf theory, is that any category of pre-sheaves carries a canonical, well, if you build a category of pre-sheaves on a monoidal category, the monoidal category lifts to the category of pre-sheaves by something called the Day convolution tensor product. And this category of standard Borel probability spaces has a monoidal structure. You take two probability spaces and the so-called product probability space based on the product measure, which is not a product in the category, but still it's still a monoidal product in the category, lifts to the category of pre-sheaves by a well-known coend formula that is due to Brian Day. But also, when you have a category of sheaves so cutting down a pre-sheaf category to sheaves, you can always restrict the monoidal product. Well, you don't restrict it, you reflect it using the associated sheaf functor. But in good situations, you end up getting not just a monoidal structure on the sheaf category, but a closed monoidal structure. The monoidal structure on the pre-sheaf category is closed, so you have a lot of nice structure here. And so here, in particular, we've got a closed monoidal structure on the pre-sheaf category. And in this case, because these properties hold of the monoidal structure on the base category of probability spaces, the monoidal properties, as well as being closed, they're symmetric, and this is the affine part of the talk. They are affine, which for a monoidal structure means that the terminal object is the unit of the monoidal structure, which is the same thing as saying you have natural projections from the monoidal structure that behave nicely with respect to the monoidal structure. And I thought this was nice at the time because I realized that if we look at the interaction between the monoidal structure and we've got the sheaves of random variables, and as I said, we have a sheaf of random variables of A-valued random variables for any standard Borel space A. And in fact, that assignment is functorial from the category of standard Borel spaces and Borel measurable maps to sheaves. So we have a nice, faithful as it turns out, functor from standard Borel spaces into sheaves. And the monoidal structure, when you look at how it combines these sheaves of random variables, so if you've got two sets of random variables and we can combine them using the tensor that we've got on the category, it turns out to be something very nicely probabilistically meaningful, which is pairs of random variables that are independent. So I thought that was really a nice interaction between category theoretic structure and probability. However, after a while trying to work with it, I came to the conclusion that it's not helpful for developing a useful axiomatization of probability theory. Because in probability theory, you really need, independence really needs to be a property that may hold or may not hold, depending on quite subtle calculational considerations. And it really doesn't seem to help at all to build independence into the type structure, so to speak. And another issue is also to incorporate the monoidal structure into the internal logic is also complicated because the functor is not fibered in the sense that it needs to be to be internalizable in the internal logic. So for those that know about modalities in type theory where similar issues arise, one has to, things get complicated if you have to deal with this sort of situation. So in the end, it turned out to be better, I found out, to just ignore the monoidal structure completely and go down a different path. So this was one of the wrong turns I took. And the moral here is, I think, don't be over-seduced by elegant category theoretic structure. So I was for at least a couple of years sort of misled by not really misled, it's a nice structure, but it didn't help in the end for what I wanted to do. So in the end, what seems to turn out to be more useful is to focus on the functoriality of this assignment from value spaces, which, as we've seen, are standard Borel spaces, to the sheaf topos, but we're now, for the axiomatization, we're working the internal logic, so the sheaf topos is now, from the point of view of the logic, our category of sets. It's our ambient world of sets. So the first axiom is simply we have a functor. For any standard Borel space, we get a set of A-valued random variables. And then, obviously, something very important that's associated with a random variable is its probability law. And the probability law assigns to a random variable a probability measure over the sigma algebra of the value space. And this is, in fact, a natural transformation, which merely says that if we push a random variable forward along a function, then the probability law gets assigned the push forward measure, for those that know about such things. So in category theoretic terms, it's very nice. We simply have a functor and a natural transformation that assigns to every random variable its probability measure of which is the law of the random variable. Okay. But then I didn't like this either, for the following reason, that in this setting, the set of random variables is only defined for very nice value spaces, namely standard Borel spaces. This is a bit restrictive. A lot of probability theoretic arguments go outside that, even if in the end you want to get back into that. And it's also clunky in that you don't want basic probability theory to depend on understanding the notion of a standard Borel space as your value space of random variables first. You'd like something more primitive. And of course, one of the reasons we're restricting to, anyway, some kind of measurable space is to get over the issue that in set theory you can, under reasonable assumptions of what you want probability measures to satisfy, you can prove that you can't assign probability measures to all subsets of, say, the set of, say, the interval or something like that with the uniform probability measure on it. So you can't measure arbitrary sets. So you have these sigma algebras that say, okay, we'll just measure the events, namely the sets in the sigma algebra. But of course, we're doing synthetic mathematics, so there's no reason to be constrained by the ZFC orthodoxy that gives rise to that train of thought. And we've already seen in our model that we don't have the axiom of choice. So we've already given up the axiom of choice. So the existence of non-measurable sets depends on the axiom of choice. And since we've given up the axiom of choice, there's no reason to be afraid of asking all sets to be measurable. So So the next thought is, why not simply allow just to have a set of random variables valued in any set A, and for any random variable we'll map it to its probability law, and the probability law is now going to be a power set measure, so a probability measure defined on the whole power set of the set. So this is, I would say, a natural mathematical idealization of probabilistic experience. You know, in probabilistic experience, we consider a set as our event and we assign it a probability. The natural idealization is just simple idealization is just to say, let's always be able to do this. But it does require, yes?
So your power set is like set theory Boolean?
Yes, because we've got classical set theory here, yeah. A Boolean topos, yeah. But it does require a change of model, because this was not modeled by the original model. But the solution is kind of very simple. It's known that one has models of set theory in which all sets are, of the reals, say, are Lebesgue measurable. If you take the original model relative to such a model of set theory, then we're in a situation that we can model what I just said. In fact, to get a model in which all sets are Lebesgue measurable, this was due to Solovay from the late 60s, published in like 71 or something like that. I don't remember exactly. Those models are very complicated, but if one just actually, if you don't require the sets to be Lebesgue measurable, but just to be nicely measurable in a weaker sense, actually you can get away with much less. And actually there's a very quite simple sheaf model, which I particularly like, and I've given some talks on it various places, but I haven't published yet, called the random topos. And this has nice power set measures. And so the well-chosen model is atomic sheaves over standard Borel probability spaces defined internally in this sheaf topos, the random model. So that's now my replacement guiding model. And so now the axioms we had before.
Sorry, Alex?
Yeah?
I'm saying that within the random topos, you're constructing a topos?
Exactly, yeah. So it's a Grothendieck topos relative to another Grothendieck topos, but you can then, if you have such a thing, it's actually just a Grothendieck topos, and it's a simple construction. But it's best to think of it that way. Okay, so our axioms now become more simply, rather than a functor from probability spaces to sets, we now simply have an endofunctor on sets that maps every set A to the set of A-valued random variables. And the probability law is simply a natural transformation from the set of random variable, well, from the random variable functor to the, again, the probability measure functor, but now it's the probability measure functor that to any set A assigns the set of all probability measures on the power set of A. This is a functor, indeed a monad, via the push forward. Okay. So then the next axioms, so we've got random variables, we've got their laws. In probability theory, we're often considering pairs of tuples of random variables, and a random variable over a tuple is the same as a tuple of random variables. And more generally, a random variable over an infinite sequence, a countable infinite sequence, is equivalent to giving a random variable on the space of infinite sequences. So that's very simply formulated in category theoretic terms, that this functor, this endofunctor, preserves countable, including finite products. And the other main structural axiom is that then we also require a property of the probability, the probability law natural transformation that assigns to every probability measure its probability law, called tautness, which has a bit of a category theoretic story to it, but that I won't go into. I think it's due to Robert Paré, this notion. So it says that certain pullback squares which express naturality conditions certain commuting squares are pullbacks in the case that you're applying the functors to a monomorphism. And as a consequence of that, the random variable functor preserves equalizers, and therefore it doesn't just preserve countable products, it preserves all countable limits. Okay, so these, I think, are nice structural axioms for a functor that constructs for any set X a set of random variables over X. And we can start exploiting these axioms straight away to define relations that are meaningful in probability theory. So a very simple one is two random variables being equidistributed or having the same probability law. Well, we have the natural transformation that assigns every random variable its probability law, so we simply ask that that natural transformation maps the two random variables to the same probability measure. Independence has the most naive definition. Two random variables are independent over potentially different value sets if for any two subsets the probability of the product is the product of the probabilities of the factors. Only just to formulate this, I'm using already the fact that the random variable functor preserves binary products here to there define the probability law associated with a pair of random variables x and y, which is, of course, by preserving products, a random variable on the product space A times B. And just to say, so here I'm really omitting an isomorphism. That's the canonical isomorphism that's product preservation. I'm going to omit such isomorphisms everywhere in the syntax on the slides, because otherwise things would become readable. I think there's some sort of nice theory there should be of justifying such notational simplifications that I don't think I've ever seen worked out, and it would be nice to know that one can systematically justify such notational simplifications. So the tautness axiom looked a bit mysterious, but what it corresponds to in probabilistic terms is that if you've got a random variable y on a value set B, and you've got a subset of the value set B that has probability 1, then the random variable y on B restricts to a random variable x on A in a unique way. And as a consequence of that, it follows that the equality of random variables is almost sure equality. Okay? So standardly in probability theory, you have almost sure equality between random variables is sort of the nice probabilistic notion of equality between random variables, but it does not correspond to equality between random variables. It's a quotient of that. We found that when we built the first model, in order to get the random variables to be a sheaf, we had to quotient by almost sure equivalence, and this is how that necessity comes into the is reflected in the axiomatization here. Okay, so we've got these structural axioms about essentially a random variable functor. The second part of the talk, I want to synthesize random variables. There's not going to be so much time in the second part of the talk, but so synthesizing random variables is constructing interesting random variables. So to begin with, let's notice that we have deterministic random variables. So whenever we have a set A and an element little x in A, there exists a delta x, like the delta function, so a deterministic value delta x, a random variable over A that assigns probability 1 to a set if and only if the element x belongs to that set. So yeah, it's the random variable that's with probability 1 takes the deterministic value little x. So one gets this because the random variable functor preserves finite products. So in particular, it preserves the terminal object. And so we have a single random variable over the terminal object, and then when we apply the functoriality to the map that maps the element of the terminal object to x, we get the deterministic random variable delta x from that. But the observation now is that actually with the axioms we've got so far, we can't prove that any other random variables exist. So our theory of random variables could be just a theory of deterministic random variables, and that's because the identity functor on sets satisfies all the axioms we've got so far. So the next part of the talk is going to be adding the axioms that allow us to construct interesting random variables. But before that, I want to have an interlude about the notions of equality and equivalence in this model. So in probability theory, there are kind of three equivalence relations between random variables. There's two random variables being actually equal, which is not interesting, really. There's two random variables being almost surely equal. And we've seen that in our model, this is equality of random variables. So that means for free, we get all the substitutivity properties we want because it's of almost sure equality, because almost sure equality is actual equality. But then there's the other very important equivalence relation between random variables when two random variables define the same probability law. And random variables have this subtlety that if you've got a whole family of random variables, you're interested in the subtle interrelationships between them, but in the end you kind of consider the family of all the random variables you've got, and you're only really interested in that family up to equality in law. Any other family that had the same joint law would be just as good. And it turns out there's a meta-theoretic substitutivity property that's valid in our model that kind of justifies this fact that one's only really fundamentally interested at the end of the day in random variables up to equality in law. And that substitutivity property is it looks like a substitutivity property for equality. So if you've got two random variables and they have the same probability law, and you have a property phi that holds for one of them, then the property phi holds for the other, except this is only valid if it's a sentence. So the formula phi cannot have any free variables or it can't make any assumptions about the world in it, so to speak. So this is a nice property of the model. So Emily in her talk talked about evil. So this is a different, it's a similar sense of evil, but it's in a different context in that the world, it would be evil to be able to distinguish between random variables that had the same probability law via a sentence, because we shouldn't, if we've got the right abstract notion of random variable, we shouldn't be able to. So this is the model has no evil in this sense. Okay, so now we get to the second part of the talk, which is how we synthesize interesting random variables that are not deterministic. We wouldn't be able to do any interesting probability theory if they were deterministic. So first we ask for a fair coin to exist. So there exists a random variable k on the two-element set that gives a probability of half to each of the two elements. So that's pretty self-explanatory, but one word of warning, this is really saying there exists a k. We're not going to, unlike we have RV as sort of part of the syntax of the language we're working with, we're not going to have k as a constant in the language, because if we did, we would violate the invariance principle that we had on the previous slide. Because if we've got a specific random variable to refer to, we can start comparing it up to equality or something like that, and violating the invariance under equality in law. And this combines with a very important axiom for constructing new random variables out of old, which is for any random variable, as the pointer, x over a set A, and any other random variable we've got to hand, we can always find a copy of the random variable x. By a copy, I mean something with the same probability law that enjoys the property that it's independent from the random variable y we've already been given. Okay. And this is going to be used in the first main construction of something that's of interest in probability theory. So in probability theory, what are called IID sequences play quite a prominent role. This means sequences of independent, identically distributed random variables. And I'm going to prove very briefly that for any random variable x over a set A, we can find an infinite sequence of random variables, xi, all over the set, each individually over the set A, of mutually independent random variables, each one equidistributed to each other and distributed to the original random variable. So the proof of that's very simple. We start off with x itself as our first random variable. And then if we've got the first I random variables in the sequence, then the independence axiom gives us so the first I go from 0 to I minus 1 here, gives us a new variable xi with the same distribution as the starting variable, and we want it to be mutually independent. So what that means is, we make it independent from the tuple of all the variables that we've got so far. Are we done? Well, at the induction step, we've just got an existence property that gives us xi. So to wrap all this up as a sequence, we use the axiom of dependent choice, and that gives us the required sequence. Okay. So in particular, if we apply this construction to the fair coin, we get an infinite sequence of fair coin tosses, which is like one of the very canonical objects of study in probability theory. And so among the things that one proves about the infinite sequence of fair coin tosses is the law of large numbers, which has a weak and a strong version. So the formulas can simply be formulated in our language. I only just want to point out that the weak law of large numbers uses only finite distributions over the infinite sequence. And that means we can formulate it with the axioms even if we only require the random variable functor to preserve finite products. Whereas to formulate the strong law of large numbers, we really need the axiom that the random variable functor preserves countably infinite products, because to state this property, so this property here is saying it holds almost surely that we have that the sequence of random variables, which is a random variable over a sequence, by the preservation of countable products, that random variable over a sequence gives us a converging sequence, and its limit is a half. So implicitly, what we're doing there is we're using the probability law associated with what you would call the uniform distribution on Cantor space, on the space of infinite sequences of coin tosses, or the Lebesgue distribution, but actually extended to all power sets. So using the preservation of infinite products to have this infinite sequence of random variables as a random variable over infinite sequences. Okay. So this is where I think things are very nice up to this point. Now, in order to get a theory that kind of does everything, we need to now deal with slightly more hairy stuff. So I have two more axioms, and then that's all the axioms. So the next one specifically refers to the notion of a standard Borel space. I don't really know how to do without that. So we for any set A, we have a set of random variables over the set. Each random variable comes with its associated probability measure, which is a power set measure. Now, it's not, there might be probability measures that don't belong to any random variable. So I'm going to call the probability measure a power set measure an RV measure if it is the probability law of some random variable. And I'm going to say that, impose the axiom that if we have a standard Borel space, so a nice probability space, one that is the Borel, one in which we have a complete separable metric space structure, and we've got the class of Borel sets associated with that. Is it really the end of?
Yeah, yeah, sorry.
Ah, okay. Right. Thank you. I misread the timetable. That's okay. Let me finish the sentence here. So as well as not going through the building up and then the cutting down stage, I also should have paid more attention to the timetable. I'm really sorry about that. Yeah, that's very bad. Well, okay. So it says the power set measure on the measure on any subset is equivalent for any subset there actually exists a Borel set that has the same measure and null symmetric difference from that set. So the measure can be approximated very closely by the Borel measure. And the last axiom is that all randomness, in a sense, derives from coin tosses. So every random variable is the push forward of a coin toss, of a push forward from a random variable that gives this uniform probability law on coin tosses. So okay, I don't have that written down, but just there's this fun, well-known quote from Einstein that God doesn't play dice. Well, in this theory, if you imagine all random variable randomness derives from God, so to speak, then this is saying, well, even if God doesn't play dice, all he can do is toss coins for randomness. But of course, throwing dice is equivalent to tossing coins, but the point is there is no randomness beyond that comes from infinite coin tosses. Okay, so I did at least get through all the axioms. So with the axioms, one can define conditional expectation, regular conditional probability measures. There's a conditional version of the existence of independent random variables axiom, and using that, we can construct Brownian motion. And this is then the ongoing in future work. I really want to, when I gave a talk on this topic 5 years ago in a workshop on categorical probability theory that was during the pandemic, so it was online. This was pretty much the same first goal for ongoing and future work. But as you saw, this work has been going on for 12 years. So I now have a one-semester sabbatical about to start. So this is a top priority now. So I'm really sorry for misjudging the time, but I think I should stop there. Yeah.
We'll take some time for questions.
Thank you. That was a beautiful talk. I have a question regarding the final sentence of your slide. The statement that the category set is a convenient category. Do you mean the actual set or the set as pictured from the inside of a base topos?
The set from the perspective of this model.
Yes,
sets
okay.
as in
Okay.
sets with these additional axioms. Yeah.
Okay, thank you.
But in the end, it's the category of sets.
Yes,
from the viewpoint of the axiomatization. Yeah.
Other questions?
Hi Alex, thanks for your talk. I just wanted to check my understanding again. You had the independence axiom, right? Is there a particular abstract notion of independence that you're using, or should I think about this as the usual definition of independence from probability theory?
Aha.
I'm trying to think about what the implications for the various levels of equality are for that.
That's a good question because, yeah, as I sort of alluded to at the beginning, my preparation of the slides was a bit chaotic. And there was supposed to be a slide with the definition of independence.
Like an axiomatic definition of independence.
Sure. Sorry,
It was the form.
Yeah.
Yes.
Oh.
No, was it? It seems to not be there. No, here it is. Yeah, it was this. So it's axiomatic.
I see.
Yeah. So it's the usual one from probability theory, except there's no sigma algebra involved.
I see. All right, cheers.
Yeah. But it turns out to be it turns out to correspond to, on the random variable sheaves, to correspond to that tensor product on the, that I mentioned before, that doesn't play a role in the axiomatization, but is still there for good structural reasons on the category.
Thank you very much. I was wondering about the invariance axiom. It seems a bit different from the other axioms.
The what
The
axiom?
invariance axiom.
Aha, yes.
Where does this play a role in the development? For what is this axiom crucial? And one could say that it should be a theorem, not an axiom. I don't know. It looks like a theorem. Better to have as a theorem rather than as an axiom.
Well, let's see if I can find it. So that's a good question. What is the invariance axiom good for? Here we are. So the question is, should it be, well, one question is, should it be a theorem or an axiom? So the theorem should be this as an inference rule. So if we can if we can prove phi of x, and we can prove that x is equidistributed to y, then we can derive phi of y. So that should hold without the axiom, probably, though I don't know how to prove it. In the model, this internal version holds. It doesn't follow from the other things. Well, I'm pretty sure it doesn't follow from the other things, so one needs to have it as an axiom, but it's not really the kind of axiom that you actually use for doing probability theory. But it's reassuring about the setting. It kind of builds into the setting that you don't have any evil constructions around that violate, allow one to violate this principle. I do have one application of it, which is using this axiom. This was in a paper I had in the LIX conference last year, I think. So using this axiom, I can derive a principle that says that independence preserves existential quantification in a certain sense. And that principle is a useful reasoning principle. I mean, you could verify that in the model separately, but that is a useful reasoning principle of the property of independence. Yeah.
Okay, yeah, I think I'll stop here and let's thank Alex again.
Thank you.